Afternoon, everyone, and sorry, we just wait for this recording message to finish. I think we've got that now. So good afternoon, everyone, and welcome to this Pipeline Industries Guild webinar. And for those of you who don't know me, I'm Norman Howell. I'm the CEO of the Guild. And today's webinar is on the recently completed Guinness World record-breaking River Humber gas pipeline project. And this will be presented by Stephen Ellison of National Grid, who is a lead project manager and has a track record of over 30 years of successful project delivery. The project itself involves tunneling 5 kilometers under the Humber estuary and inserting 5 kilometers of concrete coated steel pipe that weighed 6,500 tons, and then it was then tied into the national gas transmission system. And this section of new pipeline will ensure the security of supply for over 25% of Britain's gas, and it's replacing an existing feeder which had become exposed on the River Humber bed. And we are going to hear in detail the fantastic teamwork involved from National Grid and their contract partners, Skanska, AHAC and POR, in meeting the significant challenges faced during this unique tunnel and pipeline project, which has accumulated in the successful commissioning of the new tunnel and pipeline and the removal of the risk posed by the old pipeline crossing. So just before we start, I'd just like to advise you a few housekeeping rules. The first is if you could keep your camera off and your microphone on mute, as that just helps the flow of the presentation. There will be an opportunity to ask questions after the presentation is complete. And so to help us sort of manage the Q&A session, can I ask if you could post your questions within the chat function? And then, as you probably guessed from the beginning, please note that this webinar is being recorded and we will be posting it on the Guild's YouTube channel in a few days' time. So now I'd like to hand over to Stephen to deliver his presentation. Thank you.
Hi, good afternoon. Thank you very much. As has been introduced, my name's Steve Ellison. I'm the lead project manager for National Grid, responsible for delivery of this critical project for National Grid. I'm just going to spend the next probably 40 minutes or so going through a presentation which details some of the challenges and the successes that we've had to deliver this key project, and I'll go into some detail around that, and then obviously take the questions at the end. So without further ado, this project, so basically we are located between North Lincolnshire, a little village called Goxhill, and a place called Paul in the East Riding of Yorkshire. As you can see from the plan on the screen, the red line denotes the development consent order boundary that we were to deliver our replacement pipeline in. And I don't know if you can quite make out, but there's 2 green blobs, one in the near Goxhill and one near Paul, and they're the above ground installations that ultimately our pipe work had to connect into. So we were basically working between 2 fixed points in this location, and I'll pick up a little bit later on the sort of geography of this site, but you can see certainly North Lincolnshire there, it's a very rural area, so we've got some problems with sort of country lanes, narrow roads, etc. And then similarly over at Paul as well. So there's some logistical issues to deal with. But the red line on the plan denotes the new route. The old pipeline run in a very, very similar location, and we actually crossed that pipeline a number of times just in the way that it had been configured previously. So that's the location, and that's the estuary that we had to cross. So the reason why we're here, so the existing crossing of the Humber which was laid in 1984, is approximately 5 kilometres. It is one of the most important pipelines on the national transmission system, and it takes gas predominantly from the Easington terminal and then delivers it through into the heart of England via this river crossing. It transports at peak demand up to 25% of Britain's gas, so it is a very critical pipeline in the network. Now, over time, the Humber estuary, the riverbed has shifted. The tidal forces erode and move the riverbed, and it goes through 100-year cycles. And what happened, it had been identified that the riverbed was moving, and we've got another feeder crossing the river in a very similar location, feeder 1. That pipeline became exposed, and it actually became eroded underneath the pipe as well. So it was what they call free spanning. So a decision was made that pipeline would have to be decommissioned. During the decommissioning of that pipeline, it was degassed and purged, and then it was being filled up with nitrogen. And it actually subsequently failed when it was being charged up with 2 bar of nitrogen. So it was a real indication, whilst it was an older pipeline, that the existing feeder 9 pipeline in a very similar location is potentially at the same fate as that. So in 2009, we had to lay what they called concrete fronded mattresses above the pipeline, and we had to do that during the slack water. So it gave us around about a window of between an hour and a half to place the mattresses in sort of zero visibility. Now, that gives you some temporary sort of preservation to the pipe, but clearly it's not a long-term enduring solution. So we needed to come up with a way of replacing that pipe and taking the old one off risk. And I think I'd like to point out on this slide as well, the picture on the left-hand side is a shot from 1984 that shows the pipe stringing area, and the pipe was actually laid in an open trench across the river. And I'll pick up a little bit later on why we haven't chosen that solution for this crossing of the replacement pipeline. So we had to consider a number of options. Now, obviously, primary, we need to do this in an economical and efficient way, but we also need to select a technique that's actually physically possible to achieve, and also consider some of the long-term effects of the technique and also any environmental constraints that we may have. So one of the options that we did consider was a direct pipe method. However, at this length, just over 5 kilometres, the technology isn't quite there just yet to get a pipe of that diameter, which is 42-inch, across that distance. We also looked at an immersed tunnel. These are predominantly used for sort of rail and road tunnels. Whilst it was a possible scenario, it would have been prohibitively expensive, and obviously something that Ofgem is not keen on the bill payers to pay for something in addition to what we're trying to do, which is just replace a key transmission pipeline. So that wasn't selected. HDDs, we have done some similar sized HDDs in terms of diameter in the locality. We did a 40-inch one over at the River Ouse in around 2008. But unfortunately for a 42-inch, we've not got the ability to drive that 5 kilometre distance. So that was discounted. We also looked at an open trenching technique. Now, that gives us a number of problems. The first one really is from a long-term solutions perspective. In effect, this is what we did in 1984, and the riverbed continually moves. So that would be at risk of obviously becoming exposed again. So putting us back into the same situation a number of years down the line, potentially. So that wasn't selected because of that. And there are also quite a number of significant environmental constraints associated with this locality that it just wouldn't be acceptable nowadays to actually take that approach, which I'll pick up on in a few minutes. So our solution was to build a segment, concrete segment tunnel underneath the Humber estuary, which basically would be the world's longest pipeline river crossing in a tunnel. So it'd be 5 kilometres, just short, and it would be built in a 3.65 metre internal diameter tunnel with a 42-inch steel 70 bar pipeline inserted. And then there was a number of tie-ins at either side of the river below ground, but to the AGIs. There were two similar projects sort of out in the world, really, that we were able to reference. So there was the 4-kilometre River Ems crossing between the German and Netherlands border underneath the River Ems estuary. And there's also a 4.2-kilometre Santos crossing in Queensland, Australia. The key thing to note there is the length. So one's at 4 kilometres, one's at 4.2. We're obviously heading towards a 5-kilometre zone. So actually, this hasn't been done before at this length. So that brought its own challenges, to actually get the pipe inserted. There were some significant technical challenges. So those were the ground conditions for tunnelling, which I'll pick up on in a little bit later on, and the pipeline protection, and finally the pipe insertion. And that pipe insertion issue with the pipeline protection issue actually evolved during the detailed design process. Some of the other sort of constraints and things that we needed to consider were the environmental designations of the area. So it's probably one of the most highly designated locations in the UK. So you might think, well, it's near Hull, it's quite an industrial place, but actually this has got a number of key designations. So it's a Ramsar site, which means it's a protected wetland with a special status. It's a special protection area for overwintering birds, so it's key for the migratory winter patterns for the overwintering birds. It's a special area of conservation for flora and fauna. It's a triple SI, so a site of special scientific interest. There's a migrating birds wetland area. There's also the RSPB Paul Holmes Strays Reserve in the location. There are intertidal mudflats, which are really important for the curlews that overwinter in the area. That's one of the key sort of feeding areas for those birds. And then there's a very sort of heavily populated water bowl environment as well. And not only have we got that, but we've also got the standard, badgers and protected wildlife to look after. We've also got sort of Schedule 1 birds in there. So we've got marsh harriers in the area. So we needed to make sure that we protected those and our works didn't have an impact on those. So one of the things that we had to do was, when we built our construction compound, we had to set aside land for the land that we'd taken specifically so that overwintering birds could use it. And the way that we did that was to ensure that the sward length, the length of the grass on the fields were kept to a certain level, and the farmer couldn't use gas guns to sort of scare away any birds from the crops. And we built this large fence around the site so that when the birds were actually on the ground, the overwintering birds, they weren't affected from our site, from any noise, etc. So we had to put a significant amount of work in for the environmental considerations. And I think that really points you to one of the reasons why we didn't do the open cut again, because we would have to go through all of these areas and it just wouldn't be acceptable to do that now. But we were really proud, and the local community were really happy with the approach that we taken in terms of how we protected the sort of local flora and fauna and the wildlife. One of the other key elements to the scheme that we had to consider was flooding. So this was from two areas really. So we've got intertidal flooding from the estuary. So when you get the big spring tides, particularly with storm surges, it can overtop the embankments in the area. So we had to consider that, and we also had to consider sort of the overland flooding that had occurred previously. So on the bottom right hand side of the screen, you'll see that that's an area just near the site that actually flooded around about 2010, I think, if my memory serves me right. So it was a real potential that we could have flooding on site, and I'll explain a little bit more about that in a moment. One of the things that we had to do was, because there was such a risk of flooding, we needed to make sure that our key infrastructure was protected. So the sort of generators and the tunnel launch shaft had walls built around it to a height of 3.6 meters above ordnance datum, so that in the event of a flood warning and a flood, we basically were able to put the floodgates in and seal off those critical areas. And also our site offices and compounds were raised up to above 3.6 meters, so that if we did have a flood, we would be able to shut down the site, get everybody away, and then as soon as the flood waters have abated, we would be able to then return straight back to work without having to consider, refurbishing offices and all those sorts of things. So there were certain key aspects that had to be considered as part of the works. And one of the key things is that this is a development consent order project, which meant that a lot of these conditions were written in hard into the planning consent. So we had to discharge those consents and those requirements as part of those conditions. So it really set the standard, and we were able to demonstrate that we were complying with the planning conditions. So the worst thing that happens is when you get a combination of sort of the sort of spring tides, storm surge with high rainfall, and what that means is then we end up shutting the gates on the south side of the river, which prevents water coming inland from the river. But then what that does is it then backs up the water on the land. So all of those had to be taken into consideration as part of the works. But we were prepared. Fortunately, we only had a couple of alerts where we had to demobilise from site, but we never got to a stage where we actually got flooding on the site. But we were prepared for that. Another key aspect for this project is that we're working above an aquifer. So to actually build our tunnel, we started over at Goxhill on the south side, and we built a 210 metre long, 15 metre deep drift, which basically is a long ramp that goes into the ground. That's a sizable excavation, and to actually make the excavation, we needed to dewater. Now, to dewater the ground, obviously we draw water out, bend the water table, and it allows us to construct our pit. But because we were in an aquifer, there was a real concern that as we were close to the river, it does have a saline element to it. So the concern was that if we dewatered and drew the water out, we could then actually draw saline water in and get saline intrusion into the aquifer. So real concern for the Environment Agency was this, written really heavily into the development consent order, and we had to come up with a really innovative solution to prevent that from happening. So what we did was, when we dropped our wells in ready for our dewatering, we actually put recharge wells between our pit and the river. So any water that we drew from the ground, we then recharged back in front of us. So in effect, putting a clean water curtain between us and the river. Now that worked really effectively, and we had to have live monitoring that was fed back directly to the EA, and the EA came to site on a number of occasions with their senior management teams, and were really pleased and really praised the work that had gone on in this area. We were able to demonstrate from a live perspective the water levels, the flow rates, etc., which demonstrated that we weren't getting saline water intrusion. That was live fed back to the EA. Never been done before in that way, and it was a real success. So at the end of it, we were able to construct our large drift shaft without having any issues with the aquifer. And as soon as we'd completed the construction of that, we were able to then take the dewatering off and let the natural water levels recharge. So a real challenge for us, but really well engineered, and a successful outcome. Moving on really then, so if you can imagine, we're still in the detailed design phase here at the moment. So we're building our launch shaft, but we've got to detail design the tunnel and the pipeline around it. And during that detailed design, it transpired that we came upon an issue with what they call CP effects on the concrete, which is concrete degradation. And what that meant was that because we were going to be putting a pipeline through the tunnel itself, and we would potentially have to turn the cathodic protection system on, the action of the cathodic protection actually can degrade the concrete segments, and the higher the sort of power that you put in through the CP system, the higher the degradation that you can get on the tunnel lining. So that was a real problem for us. So during detailed design, this was identified, and we needed to come up with a solution to ensure that the 120-year design life of the tunnel wasn't affected. So in effect, the way that you minimize the effect of CP on the tunnel itself is by minimizing the need to actually have the CP sort of turned on, in effect. So what we did was we came up with a solution that in effect, we had a 42-inch steel pipe that would just be dual FBE coated, standard, UK pipelining technique. We weren't able to use sort of like the triple bonded pipe because of the issues where that can disbond and then give you sort of problems in the future. And bearing in mind that this pipe, once it's in the tunnel, it'll be sealed up and you wouldn't be able to get back to it as such. We needed to come up with a really robust solution. So what we did was we came up with a plan to concrete coat the pipes, and the sole purpose really of that concrete coating was to protect the FBE below it. So we put a further rough coat FBE coating on the double layer, which was then used to allow us to bond the concrete coating. We impinged a 70mm coating of concrete that was reinforced onto each pipe. I'll talk about that a little bit more in a moment, but one of the other key things was, so we want to make sure that the CP system is sort of passive rather than aggressive because of the 120-year design life issue. So firstly, we did that by concrete coating the pipe to prevent damage to the coating itself. We also then had our primary protection system, which was then like an anode system within the tunnel. So we've got linear anodes inside the tunnel. And then our fallback position, should there ever be a problem in the future, and when we pick that up through live monitoring of the system, we could then turn on a sort of a standard impressed current CP system, and that's the CP system that has the biggest impact on the tunnel lining degradation. So we came up with this solution that was multi-layered, but actually it transpires that by protecting the FBE in the first instance, you can get a really good coating with a real low level of sort of faults on it. Therefore, the need for the higher rate CP system is removed, therefore obviously reducing the impact on the degradation. But the problem with us going down this route, so it solved one issue, but it then gave us another problem. So firstly, we got our pipes from Europipe in Germany, and we had to get them all shipped across. So we did that, but they had to then be shipped direct to Edinburgh, where they were coated with this concrete coating. And because of the weight of that on the single pipes, then instead of transporting 3 pipes per wagon load, it meant we had to do it one pipe per wagon. So it's just over 400 pipes that had to be concrete coated and then transported to site. So you start to add that into the little, the rural location, the number of vehicle movements. It starts to put pressure on the scheme. But it was a thing that we had to do to make sure that the asset would meet its design life. And the other final thing really is that increased the tunnel pipe from just over 3,500 tons to just short of 6,500 tons. So that then gave us some issues associated when we needed to push the pipe in. So just going back to the sort of rural location, you can see here on a number of these pictures, we've got the tunnel boring machine or elements of it that needed to be transported down these sort of rural lanes. So we had to set up ourselves a one-way system. So this was the inroad, and then we had to build a temporary road through a farmer's field and an industrial estate on the outpath to mitigate some very narrow sections. When we were building the tunnel itself, just for removing the excavated material, there was just short of 10,000 vehicle movements. So that's 10,000 wagon journeys up this road, empty wagons, to then come out on the outward bound route with fully loaded with the arisings from the tunnel. We also had the segments to be brought in here, and all the stone and materials required to construct the site. So it was very challenging. And one of the things that we had to do very early on was engage well with the local stakeholders. There were a few teething troubles to start with, but we had 24-hour hotlines, and we were able to react very quickly to any concerns. And in the end, we became a very positive, from the initial phase, from the local community, we came to be a very positive player in the area, really, working a hell of a lot with the local schools and demonstrating how, we can manage large-scale construction projects in rural areas, to the point where the local councillors were actually holding us up as the examples in the area of how traffic management should be done. So some real challenges for us, but some significant wins with the stakeholders, that really, we were seen to be doing really well in the area. So I mentioned before some of the challenges with the ground conditions. So predominantly the ground where we were sort of excavating through was Flamborough and Burnham chalk, but that was overlain certainly at the Goxhill side with the glacial till, which is sort of a clay-like material. So while we were boring through with the tunneling machine, that gave us some problems initially, because the clay element was sort of clogging up our screen. So that slowed us down a little bit until we got it to the fine tune, where we needed to get to, and then we were able to get some good production. The arisings then became predominantly chalk for probably 80–90% of the drive, and that allowed us to actually take that material. You can see here in some of our bays, so the shot to the right hand side is a filter press. So the tunnel boring machine actually ground into the chalk into a slurry that was piped to the machine, and then the slurry came back from the face of the machine back to the slurry treatment plant, heavily laden with like this chalk milk. That was then pressed so it can be solidified, and it was transported from the picture on the right into the bays on the left hand side, where it was chemically tested to make sure it was within the tolerances of the requirements for removing the material. And then this material was then taken away and reused to reinstate a local chalk quarry. So over 99% of the material excavated, and it was over 190,000 tons of material in total, was actually taken away for reuse. So it wasn't deemed to be a waste. So it was a massive success really for the scheme. One of the other key things though is that on the Paul side of the river, we were going into areas which were basically, they'd been laid down from sort of from the glacial periods really, and we had to sort of cut through old incised river channels. So we had to build a reception shaft that was 15 meters diameter, 15 meters deep, and during the excavation of that we found sands, gravels, lots of fluvials and alluvials that were laid down into old riverbeds, which is not very good for a big heavy tunnel boring machine to work through. So we also found peat layers in there and old trees, from thousands and thousands of years ago, that have been preserved in those ground layers. So it was really like a layer cake really in terms of what we were going through. One of the concerns that we did have, in 1999 there was a river crossing, the River Hull, which is a tributary to the River Humber, where a tunnel was built underneath it and it actually collapsed. And the reason why that was because the tunnel itself became buoyant because of the tidal patterns, and because it was where the crown of the tunnel was, there was a peat layer, a very thin peat layer. But what happened was the movement of the tunnel actually compressed the peat layer, and it allowed a pathway then for fine blown aeolian sands to actually get inside the tunnel. And what that meant was it left a pocket of no ground around the segment ring itself, which eventually led it to collapse. So we were really focused on this scheme about that. We were really concerned because we were going through the similar ground conditions. So we ended up with a solution where we had 24-hour inspection, monitoring the tunnel inside to make sure we didn't have any material coming in, therefore pointing to a problem of having a potential weak spot then in the tunnel, which could then collapse. And we did a sort of a 100% grouting outside of the annulus of the tunnel itself. One of the other things to add was when we received the TBM at the reception shaft as well, we had to do ground treatment. So we basically drilled into the ground and pumped it in with like a grout mix to make the ground more solid through that sort of final layer cake, so that we didn't have any problems in the last sort of 10–15 meters of the drive, and we didn't have any sort of collapse around the tunnel, because that's where you're most susceptible to have those issues. So really well developed scheme, and it sort of, with the control measures we put in place, it demonstrated and it showed that we didn't have any problems. So the tunnel itself was completed in 2019 on 10th of September. It was actually launched in 2018 on the 6th of April. And you can see the first shot on the left is us lowering the front end of the machine in. And then on the right hand side is some 18 months later, when the TBM arrived within 20 mil of tolerance within the reception shaft. The reception shaft there, 15 meters deep, 15 meters in diameter, and as I say, going through the sort of very mixed ground conditions, the layer cake as such. So massive success, and we were really pleased when that did arrive. So what that meant was that we'd constructed this this tunnel sort of 5 kilometers in length. We'd done it to the right quality. We'd ensured that there was no sort of major safety incidents associated with the tunnel build. And this tunnel itself isn't sort of like a straight tunnel in the sense of it's like a bathtub curve. So we drove down from ground level at Goxhill to the tunnel portal, which was about 15 meters below ground. So we ramped down to 15 meters. Then we started to build the tunnel. That then drove down deeper. So we got to about 30 meters below Ordnance Datum, 35 meters actually below Ordnance Datum. We then travelled underneath the estuary through the deep water channel and then back up to the other side. And we then received the tunnel boring machine approximately 15 meters deep in the shaft from the previous picture. So the things I want to really call out from this shot is the quality of the tunnel build. It was done safely. It was done to the right quality. And the sort of shame really of this is that we have to then fill this in. This was really a major bit of temporary works for the scheme, just to house the pipeline. But what this did was this enabled us to put it at the right depth and prevent us having any problems in future with regard to erosion, etc. So we're now sufficiently clear of the bottom of the river for any erosion, and also if there were any sort of plans in future to maybe deepen the channel if they wanted to get shipping further down the river. So safely delivered and to the right quality. So once we built the tunnel, what we then needed to do was actually fill the tunnel itself with water. Now this water is actually purer than Buxton Spring, Evian, your tap water at home. And the reason why that is for the CP system to work correctly for the pipeline, it needed to be of a certain chemical makeup. The first element really was we needed to make sure that there was no microbiological attack that would happen in the first 200 days of the pipeline. And the way that is reduced is by removing those nutrients out of the water. So we had to actually, once we built the tunnel, we had to go back and we spent a real large amount of time and effort actually cleaning the tunnel itself with physically scraping and washing down to remove any oils that could become the food for the microorganisms that we would be concerned about propagating and growing in the tunnel, and then obviously having an impact on the steel of the pipeline itself. So that was one element. And then the water itself, we got the water from the local aquifer, but we then had to send it through quite an onerous water treatment plant to get to the right sort of chemical makeup. So that took quite a long period of time. But in effect, once that was completed, we knew then that we had the right type of water in the tunnel ready for us to push our pipeline in. And that water is continually checked sort of going forward to make sure that the sort of the chemical makeup of it stays within tolerances. And the CP system as well was designed in such a way that the sort of reactions around that were minimized. So the change to the chemical makeup, any high pH driven from any of the cables, etc., was mitigated by the CP design. So we've successfully discharged the DCO requirements. We've built the tunnel now. We've designed the pipeline and the CP system. we now got the pipeline to site, and this is just really a shot of the whole site complex. So you can see the river in the foreground. Then you can see just below that is the in effect, it's a process plant for the tunnel boring machine and all the equipment required to treat the material that came out in the filter presses and the slurry treatment plant. And then more in the foreground, you can see all our pipes strung out ready there. So these shots here are just when they were doing the original weld procedures while we were still getting pipes being delivered to site. So you can see as well to the left-hand side is the complex for the training facilities for the staff and the offices for the staff while we delivered the scheme, which is approximately 4 years. And you can see also that there's a large amount of ground there that's been built up with stone to facilitate the strength of the ground required to actually move the pipes in and do the necessary pipe stringing. This is a shot much later on, and you can see now that we've got a number of strings there already welded up. So our pipe crossing is just short of 5 kilometers. So that meant that we needed 8 pipe strings to make up the total length of the tunnel itself. So we didn't have a 5 kilometer field that we could just string it out and push it all in one go. So the pipeline was welded, tested, AUT tested, coated, and then it was then concrete coated as well for the infill sections. And all those sections were then moved across on a bespoke bogey system that allowed the pipes to move across one by one. So they were welded on the welding string and then moved across. And you can just see on the left-hand side the little yellow bogies that were used. So they were pulled across using the blue winches to the right-hand side of the shot, you can see. And they basically pulled the pipe across in a very controlled manner. So they were ready to go into the firing line, ready to shoot them into the tunnel itself. So once we'd welded it all together, each string, we'd move the first string down to the tunnel portal. So this is the drift shaft where we built the portal itself, and we've got our pipe pushing machine in here. So there's a 750 ton thruster here, and there was a 500 ton thruster further up the shaft. And that allowed us to bring the pipe into the location in a controlled manner. So we brought one pipe in, we then pushed that in, and then we brought the next pipe in behind it. We welded it, tested it, and then coated it, and then we then pushed that in again. So I'm just going to play this short video. There's no sound, but you can just see the operation. It's obviously been sped up, but this is the operation that we undertook to push the pipe in. And if you can see just in the background there, what they're doing there is they're actually putting on a polyurethane collar. So we'd fill the tunnel with water. Obviously, with it being a bathtub curve, it doesn't quite come to the very top, but it comes up halfway up to the tunnel there. And then we put a collar on there. And what that collar does, it reduces the impact of the friction of the pipe inside the tunnel as it's being pushed in. And one of the key things is, there's been a 4 kilometer and a 4.2 kilometer pipe pushed in, but there's never been one just short of 5 kilometers. And we were concerned after the development of the CP design requiring concrete coating on the pipe, what impact that would have on the pipe push and the stresses, etc. But it actually benefited in one sense. It stiffened the pipe up. But we were able to do some really sort of finite calculations to determine actually we weren't going to overstress the pipe by pushing it in, and the fact that we were in a tunnel, it sort of self-corrected itself into the bottom of the tunnel. So that was positive. But one of the other key things that we did do, because we knew the weight of every single pipe individually, they had 70 mil of concrete coating applied. Each one of those pipes were then weighed. So when they came to the stringing yard, we knew exactly which pipe was which. So we were able then to pick the lightest pipes for string 1, and then the next lightest for string 2, until we got to the heaviest pipes, which were then put in string 8. So in effect, we were pushing the sort of lightest pipes at the farthest end of the end of the pipe push, which was minimising the risk of pipe buckling, etc. So that's just a shot really to show the progress of the pipe insertions. That was just before it started, and then we completed that on the 9th of July 2020. Really happy day for the project. Came through. We were working closely with the HSE at this time as well, and we were able to demonstrate that actually we could probably push a little bit further than that than was designed, so, which was good. But what did that do? Well, that gave us the world's longest hydraulically inserted pipe in the world, measured to the exact number of 4,963.7 meters. So the team were really pleased to receive that. So, you know, the efforts of National Grid, POR and Skanska and AHAC all culminating to achieve this world record. So real accolades for everybody involved and the contract partners. So something that we were immensely proud of. But once we got the pipe into the tunnel and we got it all tied in, ready to go, we then ended up in a situation where we were actually working in midwinter. So we had to come up with an innovative solution to do our tie-ins, because we would normally just do a bypass around here like that. If I just do that on the screen, hopefully we can see that. But when we did the analysis, obviously we couldn't turn the pipeline off because it was midwinter, so we couldn't do an outage. We looked at the bypass around it, and it actually, because of the flows, it would mean that we would be at a risk of failure. We got a risk of failure of 1 in our calculations. This was due to vibration and pulsation in this area here. So it meant that we would potentially have to leave our connections until later on into the following year, which wasn't very palatable for anybody, meaning that the pipeline that was in the river would be still at risk for that sort of final winter when tidal flows are highest. So we came up with a solution that this is the above ground installation at Goxhill. So we, with great support from our operational colleagues, we were able to, this is where there was a pig trap here. So we were able to valve all this off. We took the pig trap off and we piped through, did a hot tap and piped through here, which meant that when the gas was flowing, we'd removed the pulsation issue and the vibration issue here, which meant that we were actually able to make the connections in mid-December of last year during sort of peak winter flows, which hadn't been done before. So real massive success for the team. Great collaboration. There was some sleepless nights in terms of making sure we'd got the design changes in place, etc., and making sure we had the right materials available. And there was a lot of chasing down of those elements. But we also had to consider that we needed to make sure that the existing security of this site was maintained to the same standard. So we were able to bring the pipe in through the existing emergency access gate. So we had to liaise with the HSE and our security people to make sure that we did that in a way that the site remained protected. And this is just a shot really of the sort of cofferdam that we had to put in place to facilitate those connections before those connections did take place, with all the concrete supporting the pipeline, etc. So then, you know, we'd done that, we got it all completed, we got the gas on in December last year, which was a great achievement for everybody, and then it was down to demobilisation. So the shot you saw before with all that process plant, we had to then take this back and put this back down to farmers' fields as what it was beforehand. So we had to demobilise all of this and take it away from site, which then leads to the reinstatement element of the scheme. So we've been busily redraining since spring this year, the whole area. So we've demobilised all the construction materials, and we've been busily draining the site. So the picture on the left-hand side is what we had. So that was the shot you saw before from a different angle now, looking back from the Humber estuary back down towards the tunnel entry and the pipe stringing field in the far distance. All of that had to be taken away and returned back to the shot that you've got on the right there. So I'm really pleased that last week we were able to hand the land back to the landowners for those guys now to farm the land as you would expect. So successes. So what's gone well? Well, the development consent order, the delivery of that was a big concern at the beginning because it was very restrictive and prescriptive. But actually, in hindsight, that was a very good thing because it gave everybody something really focused to go at. And once we'd completed it to the standard, there wasn't any potential delay. It was clear what needed to be done. We had fantastic stakeholder engagement with the local community. We spent a significant amount of time and effort with the local community, supporting lots of local charities. And you know, as I said before, we were held in high esteem from the local councillors as well, in terms of how to do a large scale project in a small local community. The Environment Agency and the HSE, we had regular visits from the HSE, and they were extremely pleased with what they saw. We worked really closely with the HSE to make sure that everything that needed to be and should be mitigated was mitigated. Environmental management was fantastic, well done. The pipe stringing and welding, once we got that solution in place, we really got on with that and got on with the plan to make sure that was working. The arisings management was all dealt with. As I said, 99% of the material was taken away, not as a waste, but for reuse. So that's a massive achievement for a scale of a project of this size. Clearly, the tunnel completion under the estuary safely, bearing in mind the whole tunnel collapse, that was a major milestone for us, as was the pipe insertion in relation to, you know, it'd never been done before at that distance, and also the world record. And then the connections done during the winter. Again, we were really pleased with how we'd managed to achieve that. And then, as I sort of said, finally, the demobilisation and reinstatement, we've now handed the land back, and we're just sort of clearing. We're probably on site for the next 2 or 3 weeks, just clearing up the final sort of remnants of our presence there, and then we will be away. Just very briefly, I'll just give you some facts. So the tunnel boring machine was 4.4 OD. The shield, the front bit, was 225 tons, and the total TBM weight was 510 tons. It was actually, I think it was the length of, I think it was 8 buses. So it's quite a long chain that supports the front cutting face. The ID was 3.65. The segments were 225 mil, and they were 1200 mil in length. And the tunnel length was 4862, which is slightly shorter than the world record pipe push, because that's just the length of the tunnel. The pipe was actually 100 meters longer because of where we pushed it from the shaft. Over 4,000 segments, 33,000 tons of concrete, and the excavated soil mass was 190,000 tons, of which 160,000 tons were chalk. And then the pipeline itself was inside the tunnel 4.86, what we pushed. 42-inch X65, 16 ton per pipe. It ran at 70 bar. There was just over 400 pipes. Each string was around about 624, and the pipe string was 832 tons each, equating to just under 6,500 tons. So I'll now hand back, and I'll stop sharing. For any questions.
Okay, thank you very much, Stephen. That was a great presentation. And yeah, we have got a few questions, and I'd just like to say to everyone that we've got about 10 minutes. Stephen's got to shoot off for another meeting at 2. So any that we don't get answered, I'll pass them on to Stephen, and he'll answer them and then come back to us. So the first question that we have is from Des Mooney, who says this project's very similar to a water crossing completed in Ireland, the Coombe project in 2014-2015. And were there any lessons learned from that with respect to logistics of pipe installation into the tunnel and the installation itself and the backfilling, etc., grouting?
Yeah, absolutely. So we did focus quite heavily on the Corrie project, and we did take significant lessons learned from that. So one of the key things that we found was that we were keen not to have a situation where we needed to weld the pipes inside the tunnel itself. We wanted to have the least amount of sort of person hours in there as we could. So we did all our welding above ground. That was the real key that we took from that project, was the thinking behind that, and how we could sort of minimize the amount of time spent inside the tunnel. In terms of the grouting and the backfilling, there are a number of options that we could have considered for the grouting and the backfilling, and a decision was made early on to fill the tunnel with water because of the sort of cost impact and the environmental impact of using a grout and bringing that additional grout to site as well. So we, all those considerations were brought in to come up with our final solution. When you're getting into the detailed design, it isn't always as straightforward as the decision that's been made. Sometimes can constrain you a little bit, but we'd made the decisions with the information at the time, to make that best decision with the best information available. But yeah, it was a great project to learn from, and we did learn a lot from that.
Thanks, Steve. The next question comes from D. Kennedy, and it was there any consideration into using the Humber estuary for transportation of equipment and spoil, etc.?
Yeah, there was before my time on the project, there was some consideration to see if they could bring some material in from those locations, but it would have meant us having to sort of construct another sort of structure out into the estuary. And bearing in mind the sort of environmental constraints, it was quite close, but it was sort of discounted on that because of those the potential impacts and the legislation around that. If there are other alternatives, then we should use other alternatives. There is a yard further down the river that we could have utilised, but that gave us more logistical problems than going through other smaller villages, which again we had to discount. But yeah, it did focus heavily, and we did consider that, but it was not back because of those reasons.
Okay, thanks. The next one's from John Hamilton, and it says, referring to the above ground shot of the tunnel portal, what was the smaller pipe shown running parallel to the main gas pipe within the tunnel?
So that shot actually was I think if it's the shot you're referring to is where there's a yellow pipe. That yellow pipe is actually the air intake for the TBM, for the workers at the face of the machine. So that's a tunnel in construction. It's not actually in any sort of permanent state with the pipe in. The pipes on the wall were the basically got the slurry pipe to and from the machine and the cutting face. You've got a fresh water supply and a dirty water supply.
It's John here. It was the final drawing showing the pipes coming out of the portal above ground.
Sorry. I know what you mean now. So those two, there was two black pipes. You mean, don't you? Let me just. I'll just open my presentation up again.
One of the later images.
Just bear with us 1 second. I'd like to get you the right answer. Yeah, so the images, the only pipes that were then left inside the pipe, inside the tunnel, sorry. Let's get back onto the screen. Yeah, so we've got the tunnel. We've then got the pipeline itself that's running through there. And then what we needed to do is the cathodic protection system, which I mentioned earlier on, was linear anodes, but we had linear anodes on the left-hand side and we had linear anodes on the right-hand side of the tunnel. They were actually built into trays inside the tunnel itself, but where they came up out of the ground, so we in effect, we seal the tunnel up. So you've got the pipe running through, we seal it up. We need to get the cables out. So we've got two ducts that come out from the tunnel that fed the cables out for the cathodic protection system. So those pipes that you see facilitate the linear anode cathodic protection system for the pipeline itself.
Thank you.
Yeah, thanks, Steve. Next question comes from Des Mooney. Were there any special considerations for hydro testing the tunnel section? And then he's put in brackets pipe movement restraints, test water sourcing, disposal, testing schedule, pre and post tunnel grouting, etc.
Yeah, so all of those were really sort of key in terms of how we selected the correct test pressure. So the test pressure was selected on the sort of current pipeline sort of working pressure, and obviously the uplift above that. One of the things we were concerned about was potentially over sort of pressurizing the pipe and then having an effect on the concrete lining. That was one of the considerations. We didn't pre-test the pipe above ground. There was a requirement at the start to do that, but we were able to mitigate the requirement for that with the test pressure that was selected. So, and then in terms of restraint, because of the pipe was then concrete coated, once the pipe was within the tunnel, we were able to do the pressure testing. It was sort of self-contained within the tunnel, so we didn't need to restrain it, although it did grow slightly during the test. The final grouting then of the sealing up was done post test, so it wasn't a concern that we'd then have to test it again, and it then could crack some of the grout for sealing in.
Okay, thanks, Steve. So he followed on with the question: was the tunnel grouted after pipe installation? So I guess.
So the annular, the actual annulus of the tunnel was filled with the treated water. Yeah. So that treated water becomes the annular fill. So in effect, we've got a big tunnel with a big tube with a pipeline through it that's sealed at either ends. It's now full of treated water that we are able to access and test. And then the grouting at the end, where we sealed the pipe into the end seals of the tunnel, there was grout that was put around them. That was the only sort of final grouting that we needed to do.
Right, that's great. There's a couple more, Steve, if you're okay. Yeah. One from Ben Ainsley, and he says, "Fantastic project, Steve. Thank you for your presentation. With the benefit of experience of delivering the project, what are the key things you would do differently if you had to build the scheme again?"
I'd pick probably three things that I would do differently, and that's only through the benefit of the experience of delivering the scheme more than anything else. And the first thing was, we did some early mobilisation. We saw the risk of the critical path, so we did some early archaeology and things like that. But I wish we'd have done some sort of early road improvements, the year before, so that we were able to hit the ground a bit quicker and then get into the design phases a bit quicker. That was a slight concern for us. I would also look at the shift pattern for the tunneling, probably elect a slightly different shift pattern, which give us more maintenance time, because one of the things we did, we suffered quite a bit with downtime because of things breaking down. So I'd like to try and build some different shift patterns in that gives us a bit more time to maintain the equipment. So I think we could have gone a little bit quicker, maybe not too much quicker, but a little bit quicker. And then finally, the CP degradation was a new phenomena to us, and if we'd have known that very early on, we may have done something at the DCO stage to maybe do an annular fill that wasn't specially treated water. We may have gone for a grout and embedded that at the beginning, because that would have reduced a number of factors that we had to deal with, including the concrete coating pack. We could have done away with that, but we couldn't do that at the point in time we were.
Okay, thanks. Are you still okay? There's a couple, perhaps.
Yeah.
Ali Aftab asks if you could provide a schematic sort of cross section of the concrete tunnel and pipe to show the sort of supports and tie-in, under the river. So I don't know if that's possible. Yeah,
I can certainly share a long section. I'm sure I've got a long section that we can share if you want to drop me a line now, and I can send that to yourself.
Yeah, that's great. And then he also asks about how was all that water in the how was all that water pumped in the tunnel, and is the pipe floating inside the tunnel?
So because the tunnel is like a bathtub, almost like a bathtub curve. Once we'd got the water treated, it was just very simply, it just fell in by gravity. We just pumped it in by gravity until it rose to the right level, and then at either end we had bulkheads built to make sure the water was to the level that we required it. Once we'd sealed up the ends, we then topped it up with the water. The tunnel, the pipe itself, it isn't floating. It has got an element of slight, I won't say buoyancy, but that water just does give it an element of assisting reducing the friction or the impacts of friction, but it's not floating, it's actually sat on the bottom.
Okay, thanks, Steve. One comment is from Greg Jones, and he says, as project manager of the Santos GLNG pipeline project, I'd like to congratulate Steve and his team on a job very well done. So I thought you might like to hear that one.
That's great, thank you. That's fantastic to hear. And some of the guys who worked on your project actually came across onto our project, so we did learn a lot, particularly regarding the PU collars, and we did sort of use that. So thank you very much for that, and thank you for those kind words.
Yeah, and then there's two final ones, Steve. Both from David Windsor. The first is, could the tunnel have been a smaller diameter? And then he also asked what coating system was used on the welded field joints of the pipeline.
So in terms of the diameter, if you can imagine, we've got a 5 kilometre crossing under the estuary, and we've got one way in and one way out. So basically we come out the way we go in. So there's actually some HSE tables in terms of tunnel sizing, minimum requirements. So we couldn't have gone much smaller than we actually did. We were probably just above the minimum for that size of tunnel, and that's not about the final finished product, what we're putting in there. That is just about the required safety arrangements you need to have in place when you're building a tunnel. So things like 24-hour refuge chambers, emergency systems for firefighting, and those sorts of things. So the size of the tunnel was driven by that rather than the actual asset we were putting in. Yeah. And that is I'm currently working on another project, and that same subject is quite there, for discussion at the moment.
Yeah.
But it's all about the safety of the people at the front of the machine, and absolutely rightly so.
Yeah.
And then in terms of the coating, we used for predominantly the majority of the strings, we used I can't remember the name of it now, and I should do. It was a sprayed on coating. I can't remember the name. I will come back to you with what it was. But it was a system that was sprayed on at source, and the depth was checked. When we did the 8 sections, we welded them together. We just used a standard the 2-pack for that.
Okay.
Hopefully that answers that.
Okay, that's great. So that's the end of the questions. Thanks, Steve. So basically, to conclude, for me, it's been really good to see so many members joining the webinar today, and I hope you'll all agree with me. We've had a really splendid presentation, and I'd like to thank Stephen for taking the time out of his busy schedule to provide us with such an interesting presentation. And then going forward, we've got a packed programme of events through the autumn, and the September highlights are on the 9th. We've got a webinar to be presented by Red CCTV entitled The Future of Site Security, Contactless and Carbon Neutral. And then between the 14th and 16th, the HQ staff will all be at No Dig Live in Peterborough. So come along and meet us on our stand. I'm sure we can have a chat about various aspects around pipelines. Then on 23rd, we've got another webinar on the Cobus pipe pulling, a new option for UK gas. And then finally on the 29th, we have the Northern Branch karting, which is held at Wigan. And I believe we still have a couple of carts available if anybody wants to display their Lewis Hamilton talents. So, and then finally, I'd like to just remind you that we are seeking submissions for this year's Northern Branch Norman Howe Trophy PDN competition, and the closing date for that's the 17th of September. So please get your entries in as soon as possible. And then we're also, of course, taking bookings now for the Guild Dinner in March next year. That's held in the Grosvenor House in London. So for further details of these events and our future programme, please visit our website, pipeguild.com, or look out for our posts via the email and social media. So then finally, I'd like to thank you all for attending and supporting the Guild. We value your feedback on all our events, whether it's good or bad, And in addition, please let us know what you would like us to cover within our programme going forward. We're always happy to speak with members, so please do not hesitate to contact either me or or anyone from the HQ staff. So thank you again, and I hope you all enjoy the rest of your day. Thank you very much.